120 letters into a box built for 64. That is the whole attack, and in 1988 it took down a tenth of the internet in a single night. And here's the part the textbook glosses over. The overflow does not just corrupt your data. It hands the attacker the steering wheel of the processor. And before this video ends, I'm going to show you the exact moment that happens on a real debugger on screen.
Objective 2.3 is memory injection, buffer overflow, and race conditions, and it is the densest 3 words on this exam. I'm Kai, and the fastest way in is one number. A buffer is a fixed size box in memory. 64 bytes means 64 bytes, no more.
Today we go under the hood of that box because a slide can only describe this. We are going to write the vulnerable code, compile it, run it in a debugger, and watch it break.
And let me define that first word cleanly, because it trips people. Memory injection just means getting your own data into a part of memory it should never reach, and then getting the program to treat that data as something it trusts. The buffer overflow is the door. Memory injection is what you carry through it. Same objective, 2 halves of one move.
Grace here, and the move that breaks it has a name. A C function called gets. It copies whatever the user types into your box, and it never once checks how big the box is. Put that next to a fixed buffer and you can already see the trap 2 moves ahead.
Hi all, I'm Isabella and this is not theory. In 1988, a Cornell grad student wrote a program that found a server called Fingered, handed it more text than its buffer could hold, and rode the overflow into control of the machine. It copied itself to the next server and the next, until the internet of that era simply fell over. So before we touch a debugger, let me put a face on this. The student was Robert Tappan Morris, and the worm still carries his name. This is the man whose experiment became the first internet worm. He became the first person convicted under the Computer Fraud and Abuse Act, and the bug he used, an unbounded copy into a fixed buffer, is the same bug on your exam 38 years later. The faces change, the buffer does not.
And here's the receipt that this is not a museum piece. CompTIA ranks software weaknesses every year, and in 2024, the out-of-bounds write, the family this bug belongs to, landed at number 2 on the entire list. Second most dangerous weakness in shipping software, and its ancestor is a 1988 typo.
Isabella put the question every beginner asks to the room. It's the honest one.
Yes, and it is exactly this. If buffer overflows are so old and the fix is so simple, why are they still number 2 and still on a brand new exam in 2026?
Because the language gives you 100 new ways to make the same mistake, and we'll prove it by making it ourselves. Let's open the editor.
Watch me build the vulnerable function one line at a time. First, the box itself, a character array 64 bytes wide sitting on the stack. That is our buffer, and that is the whole capacity. Now the dangerous line. I call gets and point it at the buffer. Gets reads from the keyboard until you press enter, and copies every byte straight into the box. Notice what is missing. I never told it the box is only 64 bytes.
So quantify the failure. If I type 60 characters, fine, they fit. If I type 120, the first 64 fill the box, and the next 56 keep writing into memory that was never mine to touch. Gits does not stop at the wall. It writes right through it.
And the thing that lives just past that wall is the prize. So let me draw the stack, because the geography is the whole attack. Read it bottom to top. Your 64-byte box sits at the bottom. Right above it, the saved frame pointer. And right above that, the return address, the bookmark the processor uses to know where to go when the function finishes. Overflow the box upward, and you march straight into that bookmark.
And here is the part that feels almost unfair. The processor never double-checks that bookmark. When the function ends, it just takes whatever value sits in the return address slot and jumps there, no questions asked. That blind trust is not a bug in the CPU. It is how every function on Earth returns. The attacker is simply abusing a rule the machine has to follow, which sets up the whole episode. Overwrite the return address with an address you choose, and when the function returns, the CPU jumps wherever you sent it. Next scene, we compile this thing and see the protections we have to strip off to watch it happen. Modern compilers do not want this bug to work. So before we can even see the classic overflow, we have to ask the compiler to stop protecting us. That single fact tells you how the defense story ends before it begins.
One hard line before any command runs. Everything you are about to see happens in an isolated lab on a virtual machine I own against a program I wrote to be broken. You only ever do this to a system you own or are authorized to test. We show the mechanics so you can defend the box, never to hand anyone a weapon.
So let me compile it and turn the guardrails off on purpose so the raw mechanics are visible. This is a lab move, not a production one.
Even the compiler is begging you not to do this. It printed a warning about gets by name, and we compiled anyway. Now let me prove the guardrails are actually down before we attack.
Read that report. No canary, so nothing guards the return address. No NX, so injected data is allowed to run as code. And no PIE, so the addresses are predictable. That is a 1999 machine, rebuilt on purpose, so you can see the bug the way it was born.
And here's a naming trap the exam loves. That NX bit non-executable memory is exactly the same defense Microsoft calls DEP, Data Execution Prevention. Same idea, two names. If a question says DEP and another says NX, they are pointing at the same wall. Do not let the vocabulary fool you into thinking they are different controls, and keep that word predictable in your pocket for the exam. On a modern build, every one of those three would say yes, and the classic attack would fight all three at once. We turned them off so the mechanism is clean. Scene 4 is the debate about whether that even matters.
One thing that surprises students: this is not always a museum. Your home router, your IP camera, plenty of industrial gear, they ship with these very protections disabled to save memory and cost. On those boxes, the raw overflow you are about to see is not history. It is the current threat model.
So we have a loaded gun, safety off, by design, and in a sandbox. Jasmine, there's a question sitting right here that trips people. Put it to the room before we pull the trigger.
Gladly, and it's the fair one. If real systems have canary, NX, and ASLR on, is the raw overflow wasted study time? Are you at 90% ready, or is this the 10% that decides the exam?
I'll argue that hard in a minute, and honestly, Grace is half right. But you cannot understand what a canary guards until you have seen the thing it dies to protect. So first, we watch it die.
Before we keep going, one small favor that actually moves the needle. If this is landing for you, tap like, then subscribe and turn on the bell so you do not miss the rest. 2 taps, completely free, and it pushes this in front of more people who need it.
A crash is not a failure here. A crash is the receipt that says the overflow reached all the way to the processor. So we are going to make this program die on purpose and read what the corpse tells us.
The trick is to feed it a controlled pattern, a long run of the single letter A, so that when something breaks, we can recognize our own fingerprints in the wreckage. Lead with the pattern, and the crash reads like a confession.
65 is the number to hold on to. 64 bytes fill the box exactly, and byte 65 is the first one that lands somewhere it does not belong.
And picture this the way a real analyst would. Imagine Priya, a junior application security tester on her first week, handed exactly this binary and told to prove it's exploitable before the vendor will patch it. What you are about to watch is her whole afternoon, compressed into 90 seconds. The same 3 commands she'd run.
Let me load this in a debugger and watch it die. The debugger lets us freeze the program at the instant it breaks and read every register the CPU was holding. Now I feed it 120 A's. The buffer only holds 64, so the last 56 have nowhere legal to go.
And there it goes, segmentation fault. That phrase is just the operating system catching the program touching memory it was never allowed to and pulling the plug. The crash is the alarm, not the attack.
Now the money shot. Let me ask the debugger exactly what is in the instruction pointer at the moment of death. Look at those 4 ones, 4-1 repeated. That is hexadecimal for the letter A. Our typing did not just corrupt the program. Our typing landed inside the register that decides the very next instruction the CPU runs.
Sit with what that register is saying. RIP is the instruction pointer. It is the single value the processor reads to decide what to execute next. And right now it reads our letter A. We did not break the program. We rewrote its mind about where to go.
And one naming note for the exam, because older material trips people. On a 32-bit system, this register is called EIP. On 64-bit, it's RIP, the one we just saw. Same job, the pointer to the next instruction, just a wider register. If a question says EIP, it is describing this exact attack on an older machine.
And that is the exact line the exam is testing. Corrupting data is a bug. Controlling the instruction pointer is an exploit. The overflow stopped being an accident the moment our input became the address.
Here's the beginner question worth pausing on. Why did the A's land in the instruction pointer and not somewhere harmless?
Because of the geography we drew earlier. The return address sits directly above the buffer on the stack, so a straight overflow marches right into it. The first 64 A's filled the box. The next 8 painted over the saved return address, and when the function ran its return instruction, it loaded our A's straight into RIP. That is not luck. That is the stack layout doing exactly what it always does.
And history ran this exact experiment at internet scale. July 2001. A worm called Code Red found Microsoft's web server, sent it a request padded with a long run of the single letter N, and overflowed a fixed buffer in an extension called idq.dll. Same shape as our A's, just a different letter. It hit roughly 359,000 servers in about 14 hours, defacing them with a single taunting message. No human clicked anything. One overlong request per server, and the worm owned the machine. The letter N did to IIS exactly what the letter A just did to our toy.
So the takeaway is brutal and efficient. Once your input reaches the return address, the size of the program does not matter. A 4-line toy and a global web server fall to the same 8 bytes.
Controlling the instruction pointer is only step 1. The attacker still has to point it at something useful, and that is where memory injection comes in. But there is a real fight in the security world about how much this old attack still matters. And a viewer with limited study hours needs the answer, so let's actually have it. Here's the stake. Grace thinks the classic Stack Overflow is close to a museum piece on a modern hardened system. Kay thinks skipping it is exactly how you fail the exam and miss the bug that still ships. I'll keep both of you honest and call the verdict with the sources.
Start with what actually happens on the attack side. The injection idea is simple. The attacker doesn't just crash you. They plant their own machine code, the shellcode, inside the input and aim the return address at it. So the buffer holds the weapon and the trigger at once. But 3 defenses gang up on that today. A stack canary, a secret guard value placed just before the return address and checked on the way out. So an overflow trips the alarm. A non-executable stack, the NX bit, so even injected code refuses to run. And a ASLR, which shuffles the memory map so the attacker cannot predict the address to jump to.
Hold on. Run that argument forward and it falls apart.
It doesn't though. 3 independent guards, all on by default. Make your case.
Gladly, every one of those defenses has a documented bypass, and the exam names them. Take the non-executable stack. Attackers stopped injecting code and started reusing the code already sitting in the program. It's called return-oriented programming, and it lives entirely inside 2.3. The defense didn't kill the attack, it evolved it.
Fair, and I'll concede the bypasses are real, but weigh the cost to the student. Pure handwritten shellcode against a modern hardened binary is a research project, not a Tuesday. The defenses raise the floor so high that for most desktop software, the simple version I described just bounces off.
So you two disagree on how high the floor really is. Kay, give me the counterexample.
Easy. The floor has holes you don't get to choose. Canaries protect the stack, not the heap. ASLR is weaker on 32-bit systems and leaks through other bugs. And the entire embedded world ships these protections turned off to save space. Your router, your camera, your smart doorbell. The classic overflow isn't history there, it's Tuesday.
Which is exactly why the real long-term fix is not another patch on C. It is not writing the bug in the first place. Memory-safe languages like Rust and Go check every array access, so the overflow simply cannot happen the way Gets lets it. That is why big projects are rewriting critical pieces in them.
Steelman it honestly though, because that is not a free lunch. You cannot rewrite 40 years of C overnight. Safe languages carry a learning curve and a performance cost in tight spots, and the entire embedded and kernel world still runs on C for good reasons. Safe languages are the right call for new code. For the mountain of existing code, canaries and NX are still the front line.
Before either of you closes, push on the one thing you actually agree on. Is the mechanism worth learning, yes or no?
Yes. I'm arguing it's defended, not that it's irrelevant. You still have to know the attack to know what the canary is guarding, and to know why a memory-safe language is worth the switching cost.
Then we're closer than it sounds. My whole point is the defenses only make sense once you've seen the attack they answer.
So here's the verdict, and the sources back it. CompTIA keeps buffer overflow, memory injection, and the modern mitigations all inside Objective 2.3 precisely because they are one story. The classic overflow on a hardened desktop is genuinely hard. That part of Grace's case is true. But MITRE still ranked the out-of-bounds write second most dangerous in 2024, and the embedded world runs it naked, which is Kai's case. So for the viewer with limited hours, the call is simple. Learn the attack first, then learn the 3 defenses as answers to it, and you can read any 2.3 question on the page. You don't pick a side here, you hold both.
The most famous memory bug of the last decade never overwrote a single byte. It stole 64 kilobytes of secrets just by reading. Meet Heartbleed.
And it matters for the exam because it breaks the assumption you just built. Everything so far was an overwrite input spilling past the box. Heartbleed is the mirror image, an overread, and CompTIA wants you to know both directions exist.
Let me show you the real thing, because this bug got a logo which tells you how big it was. In April 2014, this bleeding heart landed on the front page of newspapers. A vulnerability so widespread it earned its own brand. That heart lives inside OpenSSL, the encryption library running on roughly 2/3 of secure websites at the time. The bug was a missing bounds check in a tiny keep alive feature called the heartbeat. One forgotten check, half the internet exposed.
Quantify the heartbeat and the bug writes itself. The deal is simple. You send the server a small payload and a number that says how long it is, and the server echoes it back to prove the connection is still alive.
Here's the analogy that makes it click. Imagine handing a librarian a sticky note that says one word, bird, but you tell them the note is 1,000 words long. An honest librarian counts your actual words. The Heartbleed librarian trusts your claim, reads bird, then keeps reading the next 1,000 words off whatever pages happen to be lying open on the desk, and reads all of it back to you out loud.
Watch the honest version first. I send one word, bird, and I truthfully say its length is 4. The server copies 4 bytes back. Clean, correct, boring. Now the attack, and it is one number. I still send the 4-letter word bird, but I lie and claim its length is 65,000. The server never checks whether my payload is actually that long.
And here is what comes back, and it is the whole horror of the bug. The server copies bird, runs out of your payload after 4 bytes, and just keeps reading whatever sits next to it in memory. 64 kilobytes of someone else's secrets, handed over with a smile. Read that leak, another user's login, a session cookie you can replay to become them, and the server's private key, the master secret that unlocks all of its encrypted traffic. None of it was ever yours to see, and the server volunteered every byte.
And students always ask why the good stuff happens to sit right next to the payload. It's not luck. A busy web server keeps live keys, decrypted passwords, and session cookies in the same process memory it uses for everything else. So whatever the Heartbeat spills past its own payload is just the server's working memory, secrets included.
And that is why the cleanup was so painful. Patching to 1.0.1G stopped the leak, but every key that might already have been read had to be revoked and reissued, and every session cookie invalidated. You cannot unleak a secret. Once it has been out, you treat it as burned.
So name the root cause in exam language, because this is the 1-mark answer. The server trusted a length the attacker controlled instead of the length it actually received. Improper input validation, a missing bounds check, the same family as the overflow, pointed the other way.
And here's the naming trap that catches everyone, so let me just say the confusing part out loud. If Heartbleed never overwrote memory, is it even a buffer overflow, or is it something else entirely on the exam?
Precise answer, because precision is the whole point. It is a buffer overrid, a distinct subtype, not a classic overflow. Both are memory safety failures from a missing bounds check, so they sit in the same objective, but one writes past the buffer and one reads past it. If a question stresses stolen data with no crash, that is the overread, and the fix is the lesson in one line. OpenSSL 1.0.1G added the check that should have been there all along. Before copying, confirm the requested length is not bigger than the payload you actually got. Validate, then copy, never the reverse.
The last bug on this objective doesn't care about your buffer at all. It cares about your clock. It's the race condition, and it wins on timing alone.
And it's the one student's hand wave, so we'll make it concrete. The exam name is TOCTOU, time of check to time of use. The whole vulnerability lives in the gap between those 2 words.
Here's the everyday version. A bouncer checks your ID at the door and waves you in, but then walks away before you actually step through. In that gap, you hand your valid ID to your underage friend, and they walk in on your approval. The check was real. The person who used it was not the person who passed it. That is a race condition.
Picture the code version like a chess fork. A program runs as a privileged user. It checks, do you have permission to use this file? And a moment later, it opens that file. 2 separate steps. Set the trap in between them and you win. Let me run the 3 lines, because the gap is invisible until you see it spaced out. Here's the check. The check passes. The path points at a harmless file in temp, and the user genuinely owns it. So far, everything is legitimate. And then comes the gap, the few milliseconds before the next line runs.
And that is the entire move. In that sliver of time, the attacker swaps the harmless file for a link pointing at a system file they should never touch. The check already passed on the safe target. The program has no idea the ground moved under it.
So now the use runs, and it writes to whatever the path points at now, not what it checked a moment ago. The privileged program dutifully opens the system file and hands the attacker the keys. Same program, same permission, completely different victim.
Name the defense, because the exam pairs it with the bug. You close the gap. Don't check and then use, because the world can change in between. Open the file once and operate on that exact handle so the thing you verified is the thing you use. No window, no race.
And there's the broader version of that fix that shows up on the exam. Make the whole check and use into a single indivisible step, what programmers call an atomic operation, so no attacker can wedge anything into the middle. Locking mutexes, operating on a file descriptor instead of a file name. Every one of them is the same move. Remove the gap the attacker was living in.
And there is one more shape of trust, the timing, that belongs here, and it is the biggest one on the list. The malicious update. You trust your software vendor, so when their update arrives, signed and from the right place, you install it without a second thought. The attacker poisons that trusted moment. 2020, a company called SolarWinds shipped network software to 18,000 organizations, including much of the US federal government. Attackers slipped a backdoor called Sunburst into a routine update, and SolarWinds signed it with their own legitimate certificate, not knowing it was poisoned. The signature was real, the code inside was not.
And notice why every defense you were taught quietly failed here. The signature check passed because the signature was genuine. The vendor was trusted because they really were the vendor. The attack didn't beat verification. It moved upstream and poisoned the thing being verified.
So 18,000 networks installed a verified, trusted, digitally signed update and rolled out an espionage backdoor with it. Not a buffer overflow, not a race in the code. A race on trust itself, won at the one instant nobody was looking.
And that ties the whole objective into one sentence. Whether it is a 64-byte buffer, a heartbeat that reads too far, a file swapped in a millisecond, or an update poisoned at the source, every one of these is a program trusting something it should have verified. Forget the rest. Remember that, and you can read any 2.3 question on the page. So the through line of Objective 2.3 is one idea wearing 4 costumes. An overflow writes past the box. Heartbleed reads past it. A race condition strikes in the gap between check and use. And a malicious update poisons the trusted moment. Every one is a missing verification.
And here's what you keep from today. When a 2.3 question describes input reaching the return address, that's an overflow. Stolen data with no crash, that's the overrid. Timing and a swap, that's the race. You don't memorize 40 facts. You match 4 shapes.
And on the defense side, the 3 names you saw in checksec are the answer key. A canary guards the return address. NX stops injected code from running. ASLR hides the addresses, and safe functions like fgets and nstri stop the overflow at the door. Each one makes the attack harder, none makes it impossible, and that nuance is exactly what the exam rewards.
Next episode, we move from the bugs to the malware they deliver. Once an overflow hands an attacker the processor, what exactly do they upload to keep it? That is where worms, trojans, and ransomware enter the story.
If watching that GBB crash made the return address finally click, hit like and subscribe so the rest of this Security Plus walkthrough lands in your feed. And there are free practice quizzes on our cert site to drill Objective 2.3 until it's automatic.
Before you go, one we genuinely argue about. Of the 4, buffer, overflow, overread, race condition, malicious update, which one do you think bites the most real software today? Tell us in the comments and tell us why.
This is Jasmine. Thanks for watching and signing off.